two reaction. A bulky or hindered alkyl halide would have been like a slow reaction, or it doesn't happen at all. And especially if the nucleophile was a weak nucleophile. So for SN2 type reactions, we were looking for primary alkyl halide and a strong nucleophile with good leaving group and a polar aprotic solvent for the reaction to take place. So based on those conditions, when you have a tertiary alkyl halide and a weak nucleophile, the reaction, it could be slow or it doesn't take place. But experimental observation shows that this reaction is actually a fast reaction, and it takes place much faster than the bromomethane with water. So if the reaction takes place and it doesn't follow the same characteristic for SN2, it must be a different mechanism. So this reaction must follow a different mechanism. Now, what they found experimentally for this reaction of 2-bromo-2-methylpropane or a tertiary alkyl halide and water, that the rate of the reaction does not depend on concentration of the nucleophile. It only depends on concentration of the alkyl halide. So in the rate of the reaction, when you write the general rate for this reaction equals K times concentration of alkyl halide, and we don't have the nucleophile here. Concentration of the nucleophile does not appear in the rate law. So this mechanism for this reaction is actually SN1, not SN2. That means a unimolecular substitution, nucleophilic substitution reaction. So we have the S for substitution and N for the nucleophilic and 1 for unimolecular. So in the rate determining step, or the transition state of the rate determining step, only alkyl halide is involved, because the reaction, the rate of the reaction depends on concentration of alkyl halide only, and not the concentration of the nucleophile. So based on the experimental finding for this reaction, for reaction of a tertiary alkyl halide and a weak nucleophile like water, found that the rate of the reaction depends on only concentration of the alkyl halide. And the replacement of the hydrogen atom with methyl groups accelerate the reaction. That means that more substituted alkyl halide would go through SN1 reaction faster. And also, another difference between SN2 and SN1 reaction is that if the substitution is going to give you a chiral center, remember for SN2, it was a Walden inversion or umbrella effect. If you start with R reactant, you would end up with S reactant. In this case, for SN2 type, for SN1 type reactions, formation of two stereoisomer, one retention and one inversion it has been observed. So in this reaction for SN1, basically leaving group is leaving before the nucleophile comes in. The numbers that, some numbers that helps this, finding from experimental finding is that a tertiary is like a million times higher. It has million times higher reactivity compared to a primary or methyl bromide, and also a primary. So the mechanism must be different. So these are some of the facts that we know about the SN1 reactions. And based on, hopefully you have already watched the video, so you have more information about this now, that in the mechanism for SN1 reaction, leaving group is going to leave first. When leaving group leaves, you have a formation of carbocation. When carbocation forms as the intermediate, so you have the slowest step of the reaction. This is you have a EA1, you have EA2, that's where the nucleophile is coming in. And then there is a EA3 only because water is the nucleophile, and you have to deprotonate or remove one of the hydrogens. Otherwise, you could have like a two-step reaction. So if you have a neutral nucleophile that is a neutral substance like alcohol or water, there's a last step involved. You must remove the hydrogen. So in the first step, carbocation forms. Formation of carbocation based on the energy diagram that we see for SN1 type reaction. Formation of carbocation is the slowest step of the reaction, and it is the rate determining step, and the transition step of the slow step, it only involves alkyl halide. Then we have the carbocation forming. So when we have the carbocation forming, now we are in the second step. So this is the first step. In the second step, nucleophile comes in and forms bond with carbon. Water acts as nucleophile because it has two pairs of unshared electron and is willing to share a pair of electron with carbocation. And you notice that here water is a neutral compound and carbocation has a plus charge. So if you add a plus charge to a neutral compound, the plus sign is going to stay. There is really nothing you don't have a negative charge from H2O that would cancel the positive charge from carbocation. So the plus charge stays. And this plus charge is actually on the oxygen, or very close to oxygen, and that makes this molecule very unstable. Whenever you see a plus charge on oxygen, you have to do something. There should be additional step. Well, in this case, there are like two possible solutions for this. One is remove H plus. If you remove H plus, you're just removing hydrogen with the plus charge. OH would stay. Second step, or the second solution, would be remove H2O. What happens if you remove H2O? If you remove H2O, you're taking hydrogen, oxygen, and the other hydrogen, plus charge is going to stay. So if you remove H2O, basically you are pushing the reaction backward, and is going to go back to carbocation, which there is no benefit. And as a result, this removing H2O in this case is not going to work for us because it's going backward. So the other solution, removing H plus, is going to work. If there is a situation that we want H2O to leave, then we use the second solution. And we have to set the condition of the reaction in a way that H2O would leave. But in this case, H plus is going to leave. And when H plus leaves, you have a compound. Anything with the plus charge, like you have here, with the plus charge or with the plus charge, these two are not a product. They are only intermediate. And because of the charge, you cannot separate them. Since you cannot separate them, they cannot be named as a product. They are still intermediate. They are going through the next step of the reaction. But as soon as you have a neutral compound, this can be isolated and it can be purified. It is a product. So you have the product. Okay.
So, Professor.
Yes.
So another H2O molecule has to come into play to complete that.
It's the other H2O is kind of acting as a base. You do have a choice at that point. Sometimes the solvent, in this case, that the solvent is water, solvent can act as a base to remove the H plus.
Okay.
And because it's going from less stable to more stable, it's actually it's possible. So this is not very hard to do it. Sometimes you bring a base to remove that H plus. But water molecule, because has pair of unshared electrons, two pairs of unshared electron, it can act as a base and it can accept the proton because it's the H plus. Is not removing H from alcohol, is removing from something that is, so the water cannot remove this hydrogen because water is not that strong of a base. To remove this hydrogen, you need a very strong, to remove a hydrogen from the alcohol, you need very strong base like sodium, like potassium, like sodium amide. So you must use very strong base. But removing H plus from a protonated alcohol is not that hard. So you don't need a strong base. Any weak base can remove this H plus because it's going to be more stable on the product side. After you remove the H plus, it's going to be a lot more stable. So it's acting as a base. Yes, water, a second molecule of water is acting as a base to remove the H plus.
Okay, all right.
Okay. So the order of this reaction is the first order based on the kinetic, or the rate of the reaction only depends on the concentration of the alkyl halide. And the more stable intermediate, the faster the reaction, because tertiary carbocation forms faster than secondary, secondary forms faster than primary. As a result, the reaction of alkyl halide, a tertiary alkyl halide would react much faster via SN1 compared to the secondary, compared to the primary. Primary and methyl, because if you have like a methyl bromide, because if after removing the Br minus, you're going to end up with like a methyl free radical of methyl carbocation, which is very unstable. And the reason for it to be very unstable is that you do not have those supporting group. Remember from last class, I said these alkyl groups, they are known to be electron donor. So they donate electron. And when they donate electron, they are going to stabilize the carbocation. So the more of these groups you have, the better or more stable the carbocation is going to be. So extreme case, you have a tertiary versus like a methyl. And if you compare this to, there's no support for this methyl carbocation, but for T-butyl carbocation, you have 3 methyl groups that is actually giving electrons and is going to make the reaction to go fast. So for SN1 mechanism, methyl and primary alkyl halides, they don't go under SN1. Same thing for SN2, or opposite thing, for SN2, tertiary doesn't go through SN2 type reaction because of the steric hindrance that you have there. Okay, so we get two products of the substitution. If in case we have the SN1 product, if it's a chiral compound, to get two products. The reason we get two products, because in the first step of the reaction, when carbocation forms, then the carbocation, the hybridization for carbocation intermediate is a sp2 hybrid. We talked about this before briefly. The sp2 hybrid has a p unhybrid p orbital that is perpendicular to the surface of the sp2. So if you have sp2, sp2, and sp2, so if it's the hybridization for carbocation sp2, then you have a p orbital that has two loops, and nucleophile can attack the carbocation from two opposite sides. It can go from the top or from the bottom. And if it goes from the top, because your nucleophile is going to be high priority group, because is a nucleophile, is not carbon or is not hydrogen, is a nucleophile, like is oxygen compared to the carbons that you have. Oxygen has higher priority. So in going from opposite direction, regardless, if one side is going to give you R product, the other side would give you the S product. So that's why you get racemic mixture, and you get mixture of two stereoisomers with SN1 mechanism. So you get a mixture of two products. There's another problem with this, and that is the other problem with this is that we have possibility for rearrangement as well. So these are the two disadvantage of SN1 mechanism. One, if this, like in this example, that you have your reactant it contains a chiral carbon, so the product is going to be chiral, and when you remove the bromine and you replace it with the OH, the OH could go from the opposite side of leaving group or from the same side, because when the OH is coming or H2O is coming, Br is not there, so there is no interference. Even though if you had the Br, like for SN2, the electron-rich or nucleophile is not going to go from the same side that you have the Br with lots of electron and negative charge. It's just going to go from the opposite side. But for SN1, since Br leaves, there is no interference. H2O can go from two opposite side, and if it goes from two opposite side, you can get either R or you could get S product. So you get a mixture of the stereoisomers. So it's not always like 50-50. It could be like 52 to 48. It could be 55 to 45. And the reason for that is even though the leaving group is gone, but still is in the neighborhood, is not gone for, it doesn't take too much time for the bromine leave and then H2O to come in. As soon as bromine leaves, the H2O is going to come in. But even though it's not attached to it, it can be. So if there is a different number for percentage value than the 50-50, the explanation is because the leaving group still is in the neighborhood, and the nucleophile that is coming is going to be bothered by. But it's the fact that you're getting mixture of the two is because of the p orbital, and the H2O can go from either side. Okay. Questions? So if the Br is not diffused away, H2O has to wait until the Br diffuses away completely before it can come in. But it's not going to stay there because it's separated. Leaving group has gone, is separated, but still is in the neighborhood. It just needs to be diffused. It just has to move a little further away from the carbon. Okay, how do we know this reaction is the SN2 type reaction? Since we already know that is SN2, but how do we know is the SN2 type reaction? What makes the first reaction to be SN2? What factors? is going to promote SN2 type reaction for the first reaction or the first two reactions. You can respond, you can use the chat, or you can use mic to respond.
Is it because it's a primary structure?
Primary, okay,
Yes.
that's one. It's and second. Second factor. Second factor is that is a strong nucleophile, because you have more than one factor. If you bring a weak nucleophile, is not going to go through SN2, it will go through SN1. So it's a primary, but at the same time is benzylic. So if you have a plus charge here, it's going to be stable. But if you have a benzylic or you have your allylic, because allylic and benzylic carbocations are stable, if you don't use a strong nucleophile, it will go through SN1 reaction. If you use weak nucleophile, it will go through SN1 reaction. So we have to look at both factors. So if you have methanol as the nucleophile, because it's a weak nucleophile, if you have a weak nucleophile, it's going to be SN1. But if it's a strong, here you have a weak nucleophile, so is a weak nucleophile. For weak nucleophile, SN1. For a strong nucleophile, it would be SN2. If it's a tertiary, it would definitely be SN1.
Professor, would fluorine be a weak?
Fluorine is a weak nucleophile, yes. Okay. So some differences or summary of the differences between SN1 and SN2 reactions. SN2 is a one-step reaction. We had the diagram before. For SN2, you have transition state. And then for SN1, you have intermediate. You have carbocation intermediate that is forming. SN1 is two-step reaction. SN2 is one-step reaction. The rate of the reaction for SN2 depends on two molecules. It's a bimolecular rate determining step. That means both nucleophile and the alkyl halide involved in rate determining step. But for SN1, it's a unimolecular. So if it's a unimolecular, only the alkyl halide is involved in the rate determining step. There is no carbocation rearrangement for SN2 because we don't have carbocation. But when we have SN1, since carbocation forms, whenever there is a possibility of formation of carbocation, there is rearrangement. So you could have like carbocation rearrangement. When there's a carbocation rearrangement, that means that your primary carbocation by hydride shift or methyl shift can go to secondary or tertiary. Have you seen carbocation rearrangement before, or this is the first time? Did we have discussion about carbocation rearrangement before, or this is the first time?
First time.
First time. Okay. So carbocation rearrangement is a problem with the SN1 mechanism. In terms of the stereoisomers, you have for SN1, you get two products, a different percentage, but you do have both R and S product. For SN2, you get inverted configuration. So if the reactant is R, you end up with S product, and vice versa. Reactivity for SN2, less bulky it is, faster the reaction. For SN1, more substituted is going to be faster the reaction.
Professor said for SN2 is the more bulky, the faster or slower?
SN2, more bulky, slow, because we don't
Okay.
want steric hindrance. SN2 type reaction does not like the steric hindrance.
Okay.
So you have a you have alkyl halide. You just alkyl halide, or I can use a secondary alkyl halide in this case. And you add H2O. What product would you expect to get? What's going to happen if you add H2O to this alkyl halide?
Won't the bromide leave?
The bromide would leave and
You would get hydrogen bromide.
you would get OH, right?
OH, yeah.
OH. This is the expected product. Okay, expected product, but when you actually make this reaction, this alkyl halide to go through hydrolysis or solvation, is going to give you this product. So if you get like 20% of this, you would get 80% of the product. How are these two products related?
One's minor, one's major. Is that correct?
As a minor, I am minor and major. And how do we get the major product? Different carbon skeleton compared to the reactant that we start. The reactant, we had bromine on carbon number 3 or 2 from this side, okay, on carbon number 2. And here we have the OH on carbon number, the 3rd carbon from the right side. So this is actually known as the rearranged product. Rearranged product sometimes is designated by like a circular arrow, like this, rearranged product. So what is happening in this case, if you look at the mechanism for this reaction, step 1 is formation of carbocation. So we have carbocation. And on step 2, it would be bromine, OH or H2O would come in and react with this carbocation. But instead of bromine coming in with this, when bromine leaves, instead of H2O coming and forming bond with the carbocation, this is going to be rearranged. Rearrangement, there are 2 types of rearrangement. One is a hydride shift, and the other one is a methyl shift. So if you have a carbocation that is a secondary, and on adjacent carbon, there is a hydride or hydrogen, that if you replace the hydrogen with the plus charge, you end up with a tertiary carbocation. If you end up with tertiary carbocation is more stable than secondary carbocation. So this is going to be beneficial. And since is beneficial, the rearrangement is going to take place. So you are going to see the rearranged product or rearranged intermediate. So you would get, this is the rearranged carbocation that is forming. So hydrogen or hydride basically moves to the carbon that you had the carbocation, and the plus charge would move to the other carbon, and it's going to change that to a tertiary carbocation. Most of this carbocation would change to tertiary carbocation by hydride shift, and that's why you get your major product from rearranged product and the minor product from the original compound that you had, original carbon skeleton that you had. So rearrangement, possibility for rearrangement, first of all, or condition for rearrangement. First of all, it must go from like a primary to secondary or to tertiary. or it could go from secondary to tertiary. It can never go from tertiary to lower number. And if you had like a secondary to another secondary, there's not much of a benefit. Let's say if you have 4-carbon alkyl halide, and then you would solve volatilize this one, add water, the product is going to be OH. There is no reason for any rearrangement, because when the bromide leaves and you get a plus charge here, this is already secondary. Even though you have a hydride here, you have a hydride here, if this one moves, is going to end up, secondary would go to primary, and that's not beneficial. If the hydrogen on the left side moves,
This is getting out of control.
it's going to go from secondary to
Like that black sheep that went all full.
okay, it will go from secondary to another secondary, and that is not beneficial either. So there would be no rearrangement in this reaction, or for this reaction, there is no possibility for rearrangement. But for the reaction that we were talking about earlier, there is a possibility for rearrangement, because the secondary carbocation would change to a tertiary carbocation. So there is a rearranged product, possibility for rearrangement. Rearrangement, you are going to hear about in chapter 8 a lot. So I just want to make sure that you hear, then you would say, oh, we have heard already enough of it. We know what rearrangement is and when it's going to happen. You must have like a carbocation to begin with before you talk about rearrangement. So if you don't have carbocation intermediate, there is no chance for rearrangement. So there is no rearrangement. If you do have carbocation, the rearrangement should yield to more stable carbocation, not less stable. So if you have a secondary that could go to tertiary, yes, rearrangement could take place. Or if it's primary going to tertiary, yes, it will take place. The rearrangement is a result of shift. What type of shift? One is like a hydride shift. So when you say hydride shift, how is hydride different from hydrogen? You have a hydrogen atom, you have hydrogen molecule, you have hydrogen ion, you have hydride ion. So when we say hydride shift, we are talking about this. And how is this different than the other hydrogens here? This is the hydrogen, the hydride is the hydrogen with pair of electrons. So you see that I boxed this hydrogen with the shared electron. So if this hydride shifts only by 1 carbon here, okay, it's going to move to the carbon with a positive charge. The carbon that is missing or losing this hydride is losing pair of electrons, and as a result is going to gain that plus charge. The carbon that is gaining this piece, which is the hydrogen with 2 electrons, or the plus charge is going to be canceled. So that is the rearranged carbocation, okay, by hydride shift. Now, the other fact you need to know about the rearrangement is that rearrangement can only happen, or a hydrogen can move only by 1 carbon, cannot move by more than 1 carbon. Okay, so if you have this situation here, let's say you have carbon, 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 you have a plus charge here. Okay. The hydride shift from this carbon is not going to be able to jump by 2 carbon. It's not going to happen. So there would be no rearrangement for this one either. No rearrangement. Okay, no rearrangement. Because hydride cannot shift by 2 carbon. You might say, well, there is hydride on the adjacent carbon. But this one, if it goes from secondary, this is the tertiary. If it goes from secondary, then you end up moving from secondary to secondary. You have to spend some energy. And if you spend some energy, it has to pay back. The payback is, in this case, going from secondary to tertiary. But there is no payback here, because if the hydride shifts, close by hydrogen shifts, with the 2 electron, you're going from secondary to another secondary. So there is no payback. So there is no chance for rearrangement for this molecule. Okay. So hydride shift, and is only by 1 carbon distance. The other possibility for rearrangement.
Excuse me, Professor. On a hydride shift, does it also have to go from a third degree carbon to a second?
It can go from tertiary to it can go from tertiary to primary as well.
Okay, so it has to downshift one basically.
Hydrogen downshift, but hydrocarbon up, right?
Okay.
Upgrade on the on the carbo cation.
What do you mean by upgrade on the
Carbocation. Carbocation.
Yeah, what do you mean by that?
Carbocation, if it's going from secondary to tertiary, like in this case that we had the rearrangement, if it's going from secondary to tertiary, yes, rearrangement will take place, because carbocation needs to go from secondary to tertiary. Or, as you were saying, hydrogen should go from tertiary carbon to a secondary carbon.
Okay, I see.
Okay. The other fact that, or possibility for rearrangement, is rearrangement by metal shift. Okay. Rearrangement by metal shift, that would be the case that you have a carbocation here, you don't have any hydrogen on adjacent carbon, on the tertiary carbon, but there is a methyl group on this carbon of the tertiary. Okay, so what's going to happen in this case, a rearrangement can take place, but this rearrangement is not by hydride shift. This rearrangement is by methyl shift. So the methyl group with the pair of electron is going to go to adjacent carbon, would take over the plus charge, and then the tertiary would take the plus charge, would change to carbocation. And as a result of rearrangement, in this case, you would see even the carbon skeleton is changing. So you have carbon attached here, and then the plus charge moves here. So this rearrangement is by methyl shift.
And that can go from tertiary to tertiary?
This is not, a carbocation is not tertiary. Your carbocation here is a secondary to begin with, but
Yeah.
it's going to end up with tertiary. So the carbocation was secondary, now you have a tertiary carbocation.
Yeah, it's the same thing pretty much. Except
Yeah. Yes, but the difference is that in this case, yes, in this case, the shift is not a hydride shift. The shift is a methyl shift. Okay. Now, other fact that you need to know, if we had no metal here, okay, if we had no metal here, you only had ethyl group. If that was the case, then there was no rearrangement, no possibility for rearrangement, because the shift is either hydride or methyl. So either one of these two groups. So in this case, there would be no rearrangement either. No rearrangement, because you have ethyl groups attached on the neighboring carbon. There's no methyl group. So you have like an ethyl group, and ethyl group. So Those are the carbocation rearrangement, possibility and limitation. If there is no hydrogen on adjacent carbon that is going to yield to higher order carbocation, then you have to look for methyl. If there is no methyl, you give up. There would be no rearrangement. If rearrangement would yield from like a secondary going to primary carbocation, is not going to happen. There's no benefit to it. If it's going from secondary to tertiary or primary to tertiary, that is like big benefit, because stability of the new carbocation that is forming is a payback for it. Okay, so now you heard about the rearrangement. So when we say that in SN1 reaction, in SN1, there's a chance for rearrangement, carbocation rearrangement. When we say SN2, there is no carbocation rearrangement. It makes sense because there is no carbocation in SN2. Carbocation doesn't form, so there should be no rearrangement. Any questions about this summary?
How would you determine which arrangement's going to be more prominent?
First, if there is a hydride, that's better, because remember, hydrogen has atomic mass of 1. But if you look at the methyl group is carbon is 12 and 3 hydrogen, that's 15. So shifting or transporting hydrogen, it takes less energy than methyl group. That's why if it's heavier than methyl group, it's not even going to take place. Like to remove ethyl group that has 29 gram per mole, like the molar mass for ethyl group is like 29, it takes a lot of energy, and the reaction is not going to, if you provide that much of energy, it could cause, a decomposition, or it's not paying back really.
Well, my question was more relating to like the race mixture composition. Which one would be like the higher percentage? How would you know?
Oh, when is rearranged?
Yeah, is the rearrangement more like, are you gonna have a higher percentage of the rearranged?
Yes.
Okay. All right.
If the rearrangement takes place, that there is a benefit. That means that the rearranged carbocation is going to be more stable, and since it's more stable, then it's going to have higher percentage. So that would be the major product.
Okay, I gotcha.
Any other question from this table? Because it's a short and sweet table, but it's going to help you a lot of like, if you understand each step, it's going to help you a lot with the multiple choice questions. So if you have a methyl or primary alkyl halide, they would go through SN2 only. If you have a tertiary or tertiary allylic, tertiary benzylic, they would all go through SN1 only. But if you have a secondary, it would go SN1 and SN2. Okay, vinylic and arylic halide, that means this compound like this. If you have a BR on the CC double bond, is not going to go through through either SN1 or SN2, because leaving of this group, the leaving group is going to cause too much pressure. I was using this term that, let's say you have double bond here, that's lots of electron, and then you have a positive charge here, that means there's lack of electron. So this person or this group is very confused. Do I have a lot of electron around me, or I have no electron around me? So this is like a very confused state for this carbon, and it gives a lot of energy, so it makes it very unstable. So you cannot have a plus charge on a carbon that carries a double bond. And the example that I was using, I said, okay, let's say you have lots of money and you cannot spend that money, and you try to sleep hungry, is going to be very hard. I mean, if you don't have money at all, if I have no money to buy food and I'm hungry, I probably can handle it easier than if I have a lot of money, but I'm forced to stay hungry. That's very uncomfortable. It's going to put me like through a lot of stress. So this example, actually a couple years after, I used this example at Nova. A student saw me and says, "Oh, remember the rich man who sleeps hungry? Is very hard, is frustrating." It helped me like in some sort of exam, and I always remember you with this example. So a rich man cannot stay hungry, sleep hungry. I mean, that's going to be hard. A carbon-carbon double bond, this is the vinylic position. The plus charge on that is going to be very unstable. So forget about the SN1. Even SN2 is not going to lose that leaving group. Even temporary is going to be very unstable. So when it says neither one, that means you cannot have plus charge on the carbon-carbon double bond. If it's a primary, secondary benzylic or the allylic halide, it can be both of them. Depends on what. It depends. We saw the example already. I hope you remember at this point. It depends on your nucleophile. If it's a strong nucleophile, it will go through SN2. If it's a weak nucleophile, it will go through SN1. This is for primary and secondary benzylic and allylic. So, what is either or? You don't want to have two products. You don't want to have a mixture of products. You want to have like the more direct or the more strict is the formation of the product or the mechanism of the reaction, less problem you have for purification. So you know which product you already have. If you want to get like SN2, if you promote SN2, then you want to you have only one product. If you promote SN1, you have like two products. You have a R and S product, or there's the possibility for rearrangement. If you don't want your product to go through rearrange stage and you don't want to have a mixture of R and S, you probably want to make sure that your reaction goes through SN2. So how would you make sure the reaction goes through SN2 if both of them are possible? If both of them are possible, both mechanisms are possible, like for secondary alkyl halide, how would you make sure is the SN2 or the other one? Can anyone tell me what factors is going to help that you have SN2 rather than the SN1? There are multiple. You can just tell me one.
You want a stronger nucleophile?
Very good. You want a strong nucleophile. You want a strong nucleophile. Those are something that you can change. So don't use water, use hydroxide. Don't use alcohol, use alkoxide. What else you can do? How would you change the solvent?
This is for SN2?
For SN2, yes. What type of solvent would be good for SN2? Protic or aprotic solvent? Both of them polar. Polar is good for both of them, but protic or aprotic?
Be protic?
Aprotic.
Aprotic.
Aprotic. No water, no alcohol. Aprotic is going to be good for SN2, like acetone, like dimethyl sulfoxide, like methylene chloride, something that is not, it doesn't have ionizable hydrogen, okay? Aprotic solvent, you don't want this. These are protic solvent. You have SH, NH, OH. These are protic solvents, ionizable hydrogen. So if you lower the concentration of the alkyl halide, you can also, or increase the concentration of the nucleophile. Concentration of the nucleophile can help for SN2, because concentration of the nucleophile If it's higher, the rate of the reaction for SN2 is going to be greater. So you just increase concentration of nucleophile. It can go through the through SN2. So these are the factors. Just want to make sure that is also in this slide. So you want to get higher concentration of nucleophile if you want SN2. You want to get a strong nucleophile for SN2. And then for the solvent, if it's a protic solvent, it can stabilize the carbocation for polar protic solvent, because from the hydrogen side is going to stabilize the leaving group, and from oxygen side or the electronegative side of the solvent, it can stabilize the carbocation. So polar protic solvent stabilize carbocation, so carbocation feels more comfortable to form. So for SN1, you need polar protic solvent. If you want SN2, you should get polar aprotic solvent. Some examples of the protic solvent. So you have, so you don't think that you have to just talk about the water or the alcohol, like formic acid, methanol, ethanol, or if you have any type of acetic acid. So formic acid, acetic acid, or any alcohol or water. These are good examples of polar protic solvents. And protic solvents are good for, they are good for SN1. Keep that in mind. Aprotic solvents, those are good for SN2 type reaction. So if you use aprotic, it would go through SN2 type, aprotic. Okay, for the SN1 reaction, you want to make sure that the reaction is polar, because the leaving group that is leaving, it has to be stabilized by something. So since it needs to be stabilized, if you bring like a polar solvent or polar protic solvent, preferably, it's going to promote or help the leaving group to leave. So if you have a non-polar or versus polar solvent, it can also stabilize the compound in the transition state. What is the conclusion here? The conclusion is that for both SN1 and SN2, you want polar solvent. The difference is the polar solvent protic or aprotic. So for both of them, you want to use polar. But if it's protic, it would help with SN1. If it's aprotic, it would use or it would promote the SN2 type reactions. So for both SN1 and SN2, increasing the polarity is going to increase the rate of the reaction. Okay, the experimental value, I designed experiment based on this also, experiment 10. I don't know you're taking your organic 1 lab at Central or not. Experiment 10 is basically studying about the effect of solvent and temperature on SN1 reaction and SN2 type reaction, different factors that is going to affect. If you increase the polarity of the solvent in that experiment, when you increase the polarity, the rate of the reaction is going to increase. Like we go from 70% to 80% polar, the rate of the reaction, it increase, or the time for the reaction is going to drop, because it's going to stabilize the transition state for both SN1 and for SN2. But emphasizing that for SN1, you need a polar protic, for SN2, aprotic. Questions? Questions?
I think we're good.
Okay, perfect. So what do you see on this reaction? What do you see in this reaction? Is this a SN1 or SN2 type reaction? What's the mechanism?
I would say SN1 because you don't have a strong nucleophile.
Perfect. Is SN1 because your nucleophile is a weak nucleophile? And if it's a SN1, what are the steps? What's the first step in SN1 reaction?
We break
Primary
the
structure.
bromine bond and form a carbocation.
And formation of carbocation, that's the first step, formation of carbocation. So if the carbocation forms here, that's the explanation. That then we could have because it's a secondary carbocation, and the neighboring carbon, which is a tertiary carbon, there is a hydrogen that can shift. And when it does shift, it's going to bring the pair of electron, and the tertiary carbon is going to take the plus charge. So a secondary carbocation is going to rearrange to tertiary carbocation. And that's why you are getting mixture of two products. So you have a product coming from no rearrangement or not rearranged, and from a rearranged carbocation. The other example for the rearrangement of the carbocation that we talked already about it is the shift of a methyl group. So if we have a primary, in this case, we have a primary carbocation, but on the neighboring carbon, we have a methyl group that can shift, and it changes to tertiary carbocation. This is by shifting of a methyl group, so methyl shift. So you must have either hydride shift or methyl shift. If the groups that you had on the neighboring carbon, they were heavier than methyl, rearrangement would not be possible. We already looked at this table. It was just a different format, different color. So for SN2, primary or methyl alkyl halide would go faster than primary than the secondary. Tertiary doesn't go through SN2. You need a strong nucleophile. You want polar aprotic solvent. Okay, that's the part that is different. So, and you want a strong nucleophile. You want aprotic solvent. The rate of the reaction depends on the nucleophile as well as the alkyl halide. The inversion or Walden inversion or umbrella effect is being noticed here. There is no rearrangement because rearrangement only comes with carbocation. If it's SN1, you do have an intermediate, and intermediate is a carbocation. So tertiary carbocation is more stable than a secondary. secondary more stable than primary and methyl. Primary and methyl would not go through SN1 because primary carbocation and methyl carbocation, they are very unstable. They don't form. For SN1, you don't need a strong nucleophile, so weak nucleophile is good. Solvent can act as a weak nucleophile. The solvent should be protic solvent. The rate doesn't depend on the nucleophile, just the alkyl halide. You would get racemization, and the racemic mixture that you are getting is because carbocation is sp2 hybrid and the nucleophile can attack from both sides. The product is going to be rearranged if possible, if the rearrangement is a possibility. Sometimes rearrangement is not an option, so you don't have rearranged product. Okay, this chapter is known based on the 4 mechanisms, not 2 mechanisms. We already talked about SN1 and SN2 mechanisms. The other 2 mechanisms are E2 and E1. E stands for elimination, and 2, as we learned before, stands for bimolecular, and 1 stands for unimolecular. So for E2, which is elimination, what is being eliminated? If it's alkyl halide, elimination is going to be HX. Okay, HX is going to be eliminated. HX. So it's a minus HX. So for elimination, you have minus HX. Which carbon is going to lose X? X is the halide, right? Which carbon is going to lose the X? You start with the reactant. Which carbon is going to lose the halide?
The tertiary carbon.
Wherever the X is, right? So it's very obvious that this carbon is going to lose the X. If bromine is on carbon number 2, the bromine is going to leave from carbon number 2. So that's kind of a silly question, but in this case, it was a tertiary carbon that is losing the halide. And which hydrogen is going to be removed? So Br is removed, H is removed. Which hydrogen is going to be removed? If it's symmetrical, so hydrogen is not from the same carbon, it's from adjacent carbon. Okay, so to remove hydrogen, we have to look at one of these 3 groups. Now, in this case, because it's symmetrical, it doesn't matter which of this carbon is going to lose hydrogen. One of them would lose hydrogen, and if one loses hydrogen, so when Br is gone, you get a plus charge here. When hydrogen is removed, in this case, hydrogen is removed, not hydride. You see the difference? Hydrogen is removed, H is removed. So what happens to this pair of electrons? The pair of electrons is going to be dropped back in, and it forms a carbon-carbon double bond. So you basically get a negative charge with pair of unshared electron, and you have a positive charge on the neighboring carbon. The attraction between these 2 is going to cause the pair of electron to move in, a carbon-carbon double bond would form, and you get rid of the positive and negative charge, and it is stabilized. So when carbocation leaves, when carbocation forms, it makes it very unstable, but as soon as you remove a hydrogen from adjacent carbon, pair of electron would drop in and form carbon-carbon double bond. You have alkene as a product, and then you have the stabilized product. So the product of elimination of alkyl halide is alkene. So H would leave halide would leave, and then you get CC double bond. Now, how is E2 different from E1? If for E2 is a one-step reaction again. For E2, we have one-step reaction. For E1, we have two-step reaction. Okay. What is happening in E2? Hydrogen is being removed at the same time leaving group is leaving. So hydrogen is removed and leaving group is leaving. That is one step. So you have transition state. And what can we bring to remove hydrogen? Should we bring acid to remove hydrogen? Should we bring base to remove hydrogen? Should we bring alcohol to remove hydrogen? What do we have to bring in to remove hydrogen? It is H plus. You have to bring a base. If carbocation is not formed yet, and you have a leaving group has not gone yet, basically the attack is taking at the same time. You have a stable molecule that you are removing hydrogen. Your base must be very aggressive. So you have to bring a strong base. For E2, you need a strong base. Okay, you have to bring a strong base. It's going to remove hydrogen. And remember, it's only removing hydrogen, not the pair of electron, because the pair of electron drops in. And Br is going to leave, and you get alkene. The difference is if these two takes place simultaneously, it's called E2. If one takes place and then the next one is E1. So if leaving group leaves first, you have carbocation, then you have a carbocation intermediate, and the rate determining step only depends on formation of carbocation and not the base. Then we know that is an E1 mechanism. So that's the difference between E2 and E1. So for E2, both alkyl halide and base are involved in rate determining step or transition state of the rate determining step, and the rate of the reaction depends on concentration of both of them. For E1 is going to be, for E1, the rate for E1 is going to be K concentration of the alkyl halide only, and not the nucleophile. Just like SN1. So base is going to remove hydrogen from adjacent carbon, is known as the beta elimination, or the carbon that carries the alkyl group is, if you call it alpha, a carbon adjacent to that is beta. So if you say beta elimination of hydrogen, hydrogen eliminated from the beta carbon, or just remember, hydrogen is not going to be removed from the same carbon that has the halide, is going to be removed from adjacent carbon. So 1-2 elimination reaction. So that means adjacent carbon. So don't get confused, or don't be intimidated by the terms that is used. Adjacent carbon. If Br is leaving from this carbon, a hydrogen can leave from the adjacent carbon. Now, if you have two adjacent carbon, which adjacent carbon? That's something we are going to look into it. But just know that from the adjacent carbon. Why alkyl iodide is most reactive? Because iodide, we know that is the best leaving group. The better the leaving group, the faster this reaction. Okay, so that's one of the factors. We need a good leaving group. So Br leaves, the hydrogen is removed, you get a carbon-carbon double bond. We have the rate of the reaction. And for E1 mechanism, you don't have a strong base. So if you don't have a strong base, the leaving group must leave first, and that would be under the slow step of the reaction. The leaving group is leaving, and then the base is going to come in and remove hydrogen from beta carbon or adjacent carbon. Then you have. So the rate for this reaction is going to depend only on concentration of alkyl halide, not the concentration of base. The reaction is a two-step reaction. And formation of carbocation as an intermediate. So you have carbocation intermediate. Anytime there is a carbocation intermediate, there's possibility for rearrangement. You're not going to get RS or racemic product because you're going to get CC double bond. And if you have a CC double bond, you don't have a chiral compound or chiral center, so you don't worry about the R and S part. But there is a rearrangement. There's a possibility for rearrangement if you bring a weak base, if the reaction goes through a E1 mechanism. So there is chance for rearrangement. Any questions?
Professor, they don't they never take a hydrogen from the alcohol, the alpha carbon?
No. Hydrogen is always coming from adjacent carbon, or it's called a beta carbon. Now, if you have two beta carbons, like in this example, and it's symmetrical, it doesn't matter which one is going to lose hydrogen. So is this an E1 or E2 mechanism? Can you tell me? E1 or E2?
That's E2.
Perfect. Why is E2? Because you have a strong base. Okay, so if you have a strong base, it's going to be E2. And both of them, basically, for both of them, if it's tertiary better than secondary, better than primary. But if you have a strong base, it's going to be E2 mechanism. So beta hydrogen is going to be removed and halide would leave, a carbon-carbon double bond is going to form. The point of this example is that we have symmetrical on both sides, beta carbons are identical. So it doesn't matter which carbon would lose hydrogen. But if you come to face a compound that the alpha beta hydrogens are not symmetrical, or the groups attached to this carbon carrying the halide is not symmetrical, you have a methyl group and you have an ethyl group. Which one is going to lose hydrogen and which one you would, it's easier to remove the hydrogen from. If you look at the percentage of the product formed, so you get possibly you would get the two product. One carbon-carbon double bond would form between carbon 1 and 2, and that is this 20% here. You get 1, 2, and then the other one, if the hydrogen is removed from the right side of the alkyl halide functional group, and you get the carbon-carbon double bond between carbon number 2 and 3, which is this major product. Now, if everything else is the same, why your major product is the major product? What's the difference between these two? When it comes to carbon-carbon double bond, what happened? I was trying to use the, okay. So if you have a carbon-carbon double bond, for ethylene, you have 4 hydrogens. You could have like propylene, carbon-carbon double bond. You have 1 CH3, and then the rest are hydrogens. You have 3 hydrogens and 1 alkyl group. You could have 2 alkyl group attached. And for the 2 alkyl group attached, you could have CH3, both CH3s attached to 1 carbon, and then hydrogens attached to the other carbon. You could have 1 alkyl group attached to 1 carbon and the other alkyl group to other carbon, but you still have 2 hydrogens. You could have the same connection, but different arrangement, and that would be a trans structure. So this, all 3 of them is called like a 2R alkene. What does 2R alkene means? Like if we take the R as alkyl group, this alkene has only one R group attached to the CC double bond. In order to have alkene, you must have CC double bond. So this is unavoidable. You have to have these two carbon. And if you look at this structure here, only one alkyl group is attached to CC double bond. For these three examples that I have on the right side, the 1, 2, and 3, these are two R group attached to CC double bond with three different arrangements. So you have cis arrangement, two alkyl group attached to CC double bond, a trans arrangement, and then you have a geminal. Okay. So these are 2R. What would be a 3R alkene? Or how would a 3R alkene look like? I have a CC double bond. If I want to make this 3R, how would I make this 3R?
Be methyls on both sides.
Methyl, methyl, and what else? On this side, what do I have?
Methyl and hydrogen.
Methyl,
Thank you. One methyl and one
hydrogen.
hydrogen. Okay, that is the 3R alkene. And then last one, let's look at a 4R group. I have 4 alkyl group attached to CC double bond. So this is a 4R alkene. Now, based on the experimental value, because they always use experimental value to determine like either like heat of hydrogenation or other experimental value, but has been found that 4R alkene is more stable than the 3R. The 3R is more stable than the 2R trans. The 2R trans is more stable than 2R cis. The 2R cis is the more stable than 2R, I'm just going to call gem, like a geminal, then 1R. So these are the order of stability of the alkene based on number of alkyl group attached to CC double bond. Now, if you take this information, and please remember what we have here, 4R, 4 alkyl group attached. And if we say 1R, only one alkyl group attached. If we say 3R, that means 1, 2, and 3 alkyl group attached, and 1 is hydrogen. If we take this to the next slide where we had percentage difference, okay? We had major and minor product. Can you now see the difference? Why this is a major product and this one is a minor product? What makes the major product to be a major product? How are these two different, the 1-butene and 2-butene?
The carbon skeletal backbone is different.
How are they different? Can you classify them? Both of them are alkene. There are two different class of alkene based on the explanation on the whiteboard I had.
Yeah, they're both alkenes.
2-butene is symmetrical.
Can you just say based on the number of the R group?
It's 2R groups.
Those two
Okay,
are.
this is a 2R and this one is a 1R, right?
That will explain it. Yep.
Yes. So because 2R is more stable than 1R, that's why this major product is the major product. So going back to this structure that we had earlier, if it's symmetrical, it doesn't matter which hydrogen is being abstracted by the base. If it's asymmetrical, you have two different alkyl group on the left and right. the one that would yield to higher R alkene or highly substituted alkene group, alkene, is going to be the major product. This product has a name and it's known as a Sasef product. And let me see it's called a Sasef. And I was looking for the spelling. So if you haven't seen it before. Okay, so we have another example here. 1 group, 2 group, 3 group versus 2 group. So if we have a 3R versus 2R, because 3R is more stable than the 2R product, the chance of formation for 3R is greater. And the reason we have these two, because the alkyl halide that we have here is not symmetrical. We have ethyl group and we have a methyl group, or the methyl group. So these two are identical, but one of them is different. So if you remove hydrogen from the CH2, you would get the 3R, but if you remove hydrogen from CH3, you would get 2R. And since 3R is more stable than 2R, that's why the 3R is the major product and the 2R is the minor product. Is basically it yields to more stable alkene. It has to do with the stability of the product that is forming. Okay, and here is the rule for you. Whenever possible, more substituted alkene is more stable, and that would yield major product. I already explained about the R group, like if you have like 1 alkyl substitutions, or if you have like a 2 alkyl substitutions or 3, then we can expect that we get like major and minor product. But if it's symmetrical, we get only 1 product. Now, we looked at bulky base or bulky nucleophile for SN2. It says bulky nucleophile for SN2 is not good. In this case, it's not if it's a bulky, it's not a good nucleophile, but it's a strong base. So it can remove like a tibutoxide. It can remove hydrogen because it's a strong base. It's a strong base, but weak nucleophile is not a strong nucleophile, but it's a strong base. It can remove hydrogen. Now, if you have a bulky base, a strong base, then if it's bulky, it's going to look for the most accessible hydrogen, is not going to care, like it's going to give you like a 2R or 3R or more R alkene, because it's too bulky and it cannot be bothered to go in and approach the hydrogen that is sterically hindered. So it's not going to go here. Instead, it would look for most accessible hydrogen. So when it's looking for most accessible hydrogen, is going to get you a alkene that is not high substitutions alkene. So even though here we have like a 3R versus the 2R, but the 2R in this case was major product, that has to do with the bulkiness of the base. So if you use bulky base, instead of like a normal hydroxide or alkoxide, if you use like a etoxide, let's say if you use like a CH3, I don't know why my pen is giving me a hard time. CH2O is a strong base, but is not bulky. It's not like a tertiary like that. Is a strong base. This is going to give you a safe product. But if you use a bulky base, the product that is least substituted is going to end up to be major product. And we don't call it anti-safe, but has a different name. It's called actually a Hoffman product. So whenever you bring a bulky base in elimination reaction and you end up with major product that is unexpected, that product is known as the Hoffman product rather than the anti-safe, because a bulky group is looking for most accessible hydrogen. And these are some of the examples. The more substitute, if you bring a base that is not bulky, like a toxide, you get 79% of more substituted alkene, only 21% of the other one, which is less substituted alkene. But if you bring a bulky base, that is going to change and it would be opposite. The more bulky it is, okay, the more bulky the base is, lower percentage of the more safe product, but instead you would get a Hoffman product. Hoffman product is coming from most accessible hydrogen. Like in this case, these hydrogens are more accessible, but this hydrogen is more substituted, right? More accessible is going to be favored by bulky base.
What makes the car, or what makes that group more, what makes it more available?
Yeah. Okay, good question. I'm glad that you're asking. Okay. It's let's say you have a big group and trying to reach this this line of the food, right? Food is right here. This is the food table. Okay, that's the food table. There are one group, one person, and another big group reaching already into this plate, trying to get food from that, right?
Okay.
That's one that is like not accessible hydrogen, because this food is being already accessed by these other three groups. But if you look at, if you compare that to this hydrogen down here, to this hydrogen, one of these hydrogens,
Yeah.
there's only one group that is attached to it. Or this hydrogen here, there's only one group attached to it. See, this hydrogen are more accessible because it's only one person already reaching out this food. It's not like three other people.
Oh, I see. Yeah.
A bulky group can come in here and take the hydrogen and leave. So this is more accessible or less hindered hydrogen. And when we talk about less hindered, we're talking about less sterically hindered hydrogen is attached to less number of alkyl groups.
And you said the other hydrogen was more what?
This is like primary, and this is a tertiary. You could say it that way.
Yeah,
So
yeah.
removal of hydrogen from primary, meaning more accessible, from tertiary is like more hindered hydrogen. But that tertiary is more substituted. So it's going to yield to higher R group as well, more substituted alkene.
Okay.
Okay. Questions? Any other questions, class? Okay, what do you expect here? Is this a E1 or E2?
It's E1 because you have a weak
E1. It's two
weak
step.
base.
Two step E2. E1. Sorry.
It's a two-step reaction because we have weak nucleophile, right? Weak base. Water is
Weak
being
base,
used as a base. Weak base. So if it's a weak base, it's going to be, just emphasize, weak base, and it's going to be E1. So carbocation is going to form first, and then hydrogen is being removed. Hydrogen can be removed from primary carbon, or it can be removed from this secondary carbon. If hydrogen is removed from primary carbon, you get this product. If hydrogen is removed from secondary carbon, you would get the green line product. And since you have like a 3R versus 2R, this is a 2R product. This one is a 3R product. The 3R product is basically Saytzev product. So we have the Saytzev rule here that is going to remove, hydrogen is going to be removed from most substituted carbon. So you get your major product because it's more stable.
And the one with the more R groups is our major product because we have a not so bulky
Exactly.
base.
Yes. The bulkiness of the base is more important, is more significant for E2 mechanism, because you want to do both at the same time. You are bringing you are bringing the base, and the leaving group is leaving at the same time. So it's a lot more significant, but you're right. If it's not too bulky, then we are looking for the most stable product.
Professor, the top one is 2R and the bottom one is 3R, correct?
Yes, yes.
How come the bottom one is 3R?
Let's try it.
There's more CH3s.
You have 1R here, 2R here, and 3R, red colors. And then for the top one, you have a CH3 and an ethyl group, the green colors. So those are the two, and you have 2 hydrogen.
That's
So the
still
top-
clear then. But I guess it goes by CH3s only.
No, it goes by the alkyl group. How many carbon is attached to this
Okay,
CC double bond?
correct.
So you have the green one, that's 1 and 2, right?
Yes.
You have a methyl group and an ethyl group.
Yes.
Number of group is more, it takes the priority over how the size of the group.
Okay. Okay. All right.
Okay. So for the bottom one, the red color, you have 3 groups that is attached to CC double bond. You have a methyl, methyl, and methyl group. So you have 3 groups that are attached to the CC double bond.
I got it. Thank you.
You're welcome. Okay. For the E1 mechanism, which one is going to go faster? Because carbocation forms, then tertiary, allylic tertiary, benzylic, allylic, secondary, and the tertiary, all that they take the priority. The more stable the carbocation, the faster the reaction. And about the leaving group, the better the leaving group, the faster the reaction. This is for E1. You do not need a strong base for E1. The major factors are leaving group. Good leaving group is going to help, and then the degree of the carbocation that is forming. The more stable, the faster. Heat is a factor that if you look for the like a carbocation is forming, would it go through SN1 or would it go to E1? If you apply heat high heat favors elimination. So whenever you have like a situation that the reaction could go mixture of SN1 and E1, you just increase the temperature, it would favor elimination over substitution reaction. Primary alkyl halide, they would go to E2 mechanism only, but secondary and tertiary, they can go E1 or E2. But if you want to make sure it's E2, you have to bring strong base to make it E2. So E2 and SN2 can get like mixed. You get like mixture of the product, either SN2 product or E2 product. But again, if you want to favor E2, use high temperature. It's a long chapter. And
Yeah, it is.
so your time for the quiz, let me see if I can pause the